Now we turn to the segment tree. We will build one, query a range on it, and update a single point. It is a more flexible cousin of the Fenwick tree. Why go further than the Fenwick tree? The Fenwick tree supports only prefix sums directly. A range sum comes from subtracting one prefix from another. That works only because a sum can be undone. It is invertible. A segment tree is more general. It works for any operation that groups the same way no matter how you split it, like sum, minimum, maximum, or greatest common divisor. And it works over any range, not just a prefix, even for operations you cannot undo, like minimum. The price is more code, and about 4 times in array slots instead of just n plus 1, so it costs a bit more memory. The query and update cost is still big, O of log n, the same as the Fenwick tree. Choose a segment tree when the operation cannot be undone, so the prefix subtraction trick does not work. The range minimum lab later in this chapter is a good example. Let's revisit the interval tree from memory representation. Every internal node covers a range of the array. The node at the top covers the interval 4 to 7, and its stored sum is 9. To find its children, we split at the midpoint. The mid is 4 plus 7 over 2, which is 5 after rounding down. The left child gets 4 to mid, so 4 to 5. The right child gets mid plus 1 to 7, so 6 to 7. The children also have index numbers. For a node numbered I, the children are 2 times I and 2 times I plus 1. So the children of node 3 are nodes 6 and 7. Watch this carefully. The child indices are 2 times node and 2 times node plus 1. They are not 2 times node plus 1 and 2 times node plus 2. Getting this off by 1 quietly sends you into the wrong subtree. Here is the build in pseudocode. It takes a node index in the interval that node covers, low to high. If low equals high, this is a leaf, so we store A at low and return. Otherwise, we split at the midpoint, build the left child at 2 times node, build the right child at 2 times node plus 1, and then set this node to the sum of its 2 children. Notice the combine happens on the way back up, after both children are done. And here it is in C, matching line for line. stbuild takes the array, a node index, and the interval this node covers. If low equals high, this is a leaf. So the node holds one element, add low, and we return. Otherwise, we compute the midpoint, written to avoid overflow. We build the left child at index 2 times node, covering low to mid. And the right child at 2 times node plus 1, covering mid plus 1 to high. Those two index formulas are the same heap arithmetic from chapter 12. Then we combine. This node's value is the sum of its 2 children. Build costs big O of n. Every node is visited once, and there are 2 n-1 nodes in total for n leaves. Let's query the range 2 to 5. We start at the root, which covers 0 to 7. It only partly overlaps 2 to 5, so it is a partial node. We cannot use it directly. We must go into both of its children. First child, the node 0 to 3. It also partly overlaps 2 to 5, so it is partial too. We go one level deeper. Its left child covers 0 to 1. That is completely outside 2 to 5, so we prune it. We never open it and it adds nothing. Its right child covers 2 to 3. That sits fully inside 2 to 5, so it is an inside node. It hands back its stored sum, which is 5. Our running result is now 5. Back up and over to the other side. The node 4 to 7 partly overlaps 2 to 5, so it is partial. We go into its children. Its left child covers 4 to 5. That is fully inside 2 to 5, so it hands back its sum, which is 9. Our running result is now 5 plus 9, 14. Its right child covers 6 to 7. That is outside 2 to 5, so we prune it. It adds nothing. So only 2 nodes ever contributed, 2 to 3 and 4 to 5. 5 plus 9 is 14. Notice we touched only a handful of nodes, not every element. That is the big O of log n speed. Here is the query in pseudocode, and it has exactly 3 cases. First, if the nodes interval does not overlap the query range at all, return 0, the identity for sum. Second, if the nodes interval is fully inside the query range, return the node's stored value and do not descend at all. That second case is where the speed comes from. And third, otherwise the node partly overlaps, so we split at the midpoint and add both children's answers. The C version. ST query takes the node, the interval it covers, and the query range L to R. Case 1, no overlap. Return 0. Note 0 is the identity for addition. For a minimum tree, it would have to be a large sentinel instead, which is exactly what lab 3 changes. Case 2, fully covered. Return the stored value and stop. No descent, no rescanning. Otherwise, partial overlap. We split at the midpoint and add the 2 children's answers together. The cost is big O of log n at most 2 nodes per level are only partly covered, so the recursion touches a constant number of nodes per level, over log n levels. Let's change one value. We set at index 3 from 6 to 100. This touches only the single path from the root down to that leaf. First, we descend to the leaf, which covers 3 to 3, and overwrite it. 6 becomes 100. Now we walk back up. The leaf's parent covers 2 to 3. It recombines its 2 children. Its left child is -1 plus the new 100 gives 99. Its old sum was 5, so 5 becomes 99. One level higher, the node 0 to 3 recombines. Its children are 5 and 99, which gives 104. Its old sum was 10. The chain keeps going up to the root, which is not drawn here. The root recombines 104 plus 9, which is 113. Its old sum was 19. So a point update walks exactly one path from the root to the leaf. That is big, O of log n nodes, each one recombining its 2 children on the way back up. Here is the point update in pseudocode. If low equals high, we have reached the leaf, so we overwrite it and return. Otherwise, we split at the midpoint and descend into whichever single child contains the index. Only one child, not both. And then, on the way back up, we recombine this node from its 2 children. That last line is what keeps every ancestor correct. The C version. ST update takes the node, its interval, the index to change, and the new value. If low equals high, we are at the leaf. So we overwrite it and return. Otherwise, we compute the midpoint. And if the index is at or below it, we descend left only. Otherwise, right only. 1 child per level, which is what makes this a single root-to-leaf path. And then the recombine, on the way back up. Every ancestor of the changed leaf gets its sum refreshed. The cost is big O of log n, 1 root-to-leaf path, recombining each ancestor on the way back. A learning check on those intervals. For an 8-element array, what interval does the node with low 4 and high 7 split into for its 2 children? pause and work it out. The answer, mid is 4 plus 7 minus 4 over 2, which is 5. So the left child covers 4 to 5, and the right child covers 6 to 7. That is the same node we saw earlier in the memory section. Let's run the segment tree. We use the same 8 numbers as before: 3, 2, minus 1, 6, 5, 4, minus 3, 3. First, we build the tree. We call sendBuild starting at node 1 over the range 0 to n-1. Then we ask a range query. We print the query of 2 and 5. Next, we change one element. We call sendUpdate to set at index 3 to 100. Its old value was 6. Then we query again. We print the query of 2 and 5 once more, and also the query of 0 and 7, the whole array. Look at the output. Before the update, the query of 2 and 5 is 14, matching the trace we did earlier. After setting at index 3 to 100, the query of 2 and 5 is 108. That is minus 1 plus 100 plus 5 plus 4. And the query of 0 and 7, the whole array, is 113. That is the old total 19, minus the old 6 plus the new 100.